So now that we have seen the microscopic version of, the macroscopic version of ideal gas law, which again has to do with the fact that we're outside looking at the gas and we're looking at more of the macroscopic quantities that we can measure. Again, things like the pressure, the volume, and the temperature. So now we want to actually go inside of the box and see what's happening from more of a statistical standpoint. So basically, again, what is happening for each individual atom or molecule that's actually flying around inside of this box. Now, as I mentioned last time, we have to do this basically statistically. We'll talk about how that works here in a minute. Because, again, typically we're going to have some outrageous number of particles. For example, we had 1 mole of particles. That's 6 times 10 to the 23rd number of particles in there. And that's just something ridiculous that we can't follow all of those different particles. So basically, we have to do things statistically and kind of talk about, on average, what are things actually doing. So, again, the key part here is we're going to again look at a dilute gas. Again, an ideal gas. So in this case, we have a large distance between particles, and they're only interacting gravitationally. So let's look at one particle. Say here's my particle. This thing has a mass of m. And let's say initially it's moving in this direction with some velocity v. Okay. So what's going to happen then is that this particle is going to come this way. So say here's my particle. It's going to come here, hit the side of the board, which in this case is the side of the box, make an elastic collision. So we're going to assume that this is an elastic collision. So in this case, this thing's going to hit, let's see if I can follow my trajectory here, but this thing is going to hit something like here, and then it's going to bounce off in this direction, hit this side of the wall, bounce off, and then come back, and then hit this side of the wall at some random place up here. So what's initially happening is initially there is a momentum in this direction initially, so this is the direction by momentum. Afterward it makes an elastic collision, so it's going to bounce off in this direction, with the same amount of momentum at exactly the same angle. So whatever angle this is exactly the same angle that this is. So here, if we apply conservation of momentum, we can see here is that what? Initially it's moving in this direction in the y. At the end it moves this direction in the y, which means the change of momentum in the y direction is actually equal to 0. So my change of momentum in the y is equal to 0. But in the x direction, initially it's moving this way, afterward it's moving this way. So if I take this minus this, well, that's the same thing as this plus this, which means its change in momentum in the x direction is simply equal to twice of whatever the initial momentum was. Right? So let's call this the initial momentum in the x direction. So this is twice the mass times the x portion of the velocity. So this guy's going to come hit, bounce off, again, come back over here, hit, and then come back over here. And let's say our box in this case has a length of L, or my chalkboard has a length of L. So the time it takes for this thing to make 2 consecutive collisions, so this one followed by this one against the same exact wall, then is going to be, well, the time it took for this thing to travel that total distance. Well, in this case, it travels this distance, which is L. Travels again this distance, L. So the total distance it's going to travel is 2L. And that must be equal to, using kinematic equation number 2, the initial position, which I can call 0, times then the initial velocity times the time, plus the acceleration. Well, here the only acceleration it's going to feel is when it has that acceleration, which only acts over the time of the collision, which means on average the acceleration is only going to be equal to 0, which means that from here we can find the time, where the time then is going to be equal to twice length divided by the x portion of the velocity. Now, from here, we can then find the force on this particle as it makes a collision with this wall. Right? So first it makes a collision, comes back, hits over here, comes back over here, makes another collision, which means that the force then, at least in the x direction, is then equal to what? According to Newton's second law, this is the change of momentum in the x direction divided by the change in time. So from here, it's going to be the same thing then as twice the mass times the velocity in the x direction divided by the time, which is 2 times the length times then the x portion of the velocity. 2's are going to cancel. This is going to be the same thing then as m times the x squared divided by the length. So this means then that what? The force that this particle feels by bouncing in this direction and then bouncing in this direction again is exactly equal to the force that the wall feels, in this case in this direction and in this direction, because we know that's what the total impulse has to be equal to 0, so those two forces have to be in opposite directions, which means that this is the force on the particle, but it's also the force on the wall, right? So more appropriately, this is the force on the wall. So this is then the force that the wall feels from these two consecutive collisions. Now from this, what we also know is if this wall over here also has a cross-sectional area of A, we can then determine the pressure on the wall by simply taking this force and dividing by the area. But this is the force by this single mass here. But inside of here, I have a collection of n number of masses, which means that the force that this wall feels then is going to be the sum of all these possible forces, which are being results from this thing being hit by all these different masses. So this means then that the net force, let's do it this way. So this means then that the net force on the wall is then going to be equal to the sum, at least the net force in the x direction, so let's call this net, is then going to be equal to the sum of then the average force from all these individual forces. So we're going to average all this over all possible different velocities, because each one of these different particles could have a different velocity. Now, on average, each one of those are going to have, on average, the same velocity, though, which means that if there are n number of particles, this is going to be the same thing then as n times the average force, which then is going to be the same thing then as n, which again is the number of particles, times then the mass times the average velocity squared in the x direction, divided by simply the length of the box. So again, this is then the average force that this wall over here, or this wall over here, or even the one on top, are feeling based off of n number of particles constantly colliding with the wall. Now again, since we have the force, or at least the net force, we can now determine then the pressure. So again, we know the pressure in this case then is going to be the x portion of the force divided by the area. So it's going to be the same thing then as the number of particles times the mass times the average velocity in the x direction squared divided by the area times the length. But in this case, if I know the area and I know the length of the box, I also know the volume. So this is actually the same thing then as what? N times m times the x squared, all divided by the volume. Now, this is starting to already look like our ideal gas law. So again, what we know from Boyle's law is what? That the pressure goes inversely proportional to the volume, which is something we saw in Boyle's law, which we're already actually seeing here. Now, one other thing we can notice here is, though, this term, m times the x squared, actually looks like the kinetic energy. But it would be the kinetic energy if this was v squared, not vx squared. So again, this is the average velocity. This is the average of the square velocity in the x direction. Now, what would then be the average of the square velocity in the y direction and the average of the square velocity in the z direction? So what I mean by that is, let's say I walk into this room before I start waving my arms around and kicking and screaming and doing all the different things that I usually do, where this room just had air. Well, if I measure the velocity of air in all different directions, so if I measure it, say, in the x direction, measure it in the y direction, and then measure it in the z direction, what I would find then is that what? The average of the square of the velocity in all different directions are exactly the same. And how do I know that? Well, I know that because if I originally walk in this room, I don't feel an air draft in a particular direction. Right? I don't feel wind blowing this way, or this way, or this way. All the air is possibly moving in all different directions, but it's moving equally in all different directions, which means that I don't feel an actual flow of air, which is why I can actually say that the square, or the average of the square, in all different directions is exactly the same. Okay. Now, another thing I can know, though, is that what? The average velocity in all directions is actually 0, and I know that because the average velocity this way is the same as the average velocity this way, which means that the total velocity is going to be equal to 0. So that's why we're actually using the average of the square. So good. So in this case, what we know then is that the average of the square of the velocity then is going to be the average of the x component velocity squared, the y component squared, plus the z component squared. But again, each one of these has exactly the same value because the average in all different directions is exactly the same. So this is actually going to be equal to 3 times the average of the x portion squared. So using this, I can actually then rewrite this guy, this piece for now, as being equal to, what, 1/3 of the number of molecules times m times the average of the square velocity divided by the volume. To make this kinetic energy, I'm simply going to multiply top and bottom by 2. So this is now going to become equal to 2/3 of then n divided by the volume times then the average translational kinetic energy. So what this says then is what? What we actually measure as pressure in this box. So again, if I go back to the box, so here's my box. What we actually measure the pressure of this box to be is actually all the random collisions that all of these different molecules are making with the walls bouncing off, right? Now what this is saying then is that what? The pressure goes up as the average kinetic energy goes up, which means that as the velocity increases, that means the number of collisions that these guys are making per unit time is actually increasing because they're moving faster. So the amount of time it takes for this guy to go from here to make a consecutive collision is now much shorter, which means that there's more collisions which are happening, which means that the force is going to increase also because the change of momentum is also bigger. Which means that as, again, the kinetic energy goes up, the pressure then has to go up. Nice. So this is what this actually means. Now, again, this looks like the ideal gas law because now what it's saying is that the pressure times the volume is equal to the average kinetic energy. So let's write it in that form. So let's rewrite this. So now we can write this as the pressure times the volume is equal to 2/3 times the number times then the average kinetic energy, or in this case, average translational kinetic energy. But from the ideal gas law, what we also know is that PV is equal to NKB times T. So let's use that here. So we can replace this then with N times KB times T is then equal to 2/3 times N times the average translational kinetic energy. So again, the N's are going to cancel. So what this says then is that what? 3/2 times KB times T then is equal to the average translational kinetic energy. So I mentioned this before, and now we can actually see this. What we said was that temperature is actually related to the kinetic energy of the molecules which are moving on the inside. So what this means then is that 3/2 kBT is actually equal to the average translational kinetic energy. So again, what I interpret to be temperature in this room has to do with how fast the air molecules are moving in this room. The faster they're moving, the higher the temperature is because they're moving more, they're carrying more kinetic energy. In that case, when they make collisions with me, in that case, they're transferring energy to me, which I then take to be temperature. Or when I just measure simply the temperature of this room, what I'm measuring then is the average kinetic energy, which means that I'm measuring its temperature. So again, its temperature is directly related to the average kinetic energy. Now let's go a step further. So this guy we can write as 1/2 the mass times the average squared velocity, which is something which we end up calling 1/2 the mass times the RMS velocity squared. So from here, we can find then is that these 1/2s are going to cancel. So we can determine what is the RMS velocity of the gas. So in this case, our RMS velocity is then equal to what? 3 times kb times t divided by the mass of the particle square rooted. So this is what's known as the RMS velocity. So what is RMS velocity? So RMS velocity is defined as the square root of the average of the squared velocity. So this is what we call the RMS velocity. So, get a little bit understanding of what the RMS velocity is. Let's take a look at what's known as the Maxwellian speed distribution. So the Maxwellian speed distribution says that for a gas, I can look at then the velocity versus the probability, or you can think of this as the number of molecules. So what the Maxwellian speed distribution says is that for zero velocity, basically I have no particles which are moving. Okay? So basically I have zero number of particles which are moving. Okay? Now, as the speed starts to increase, this thing is actually going to do this until I reach some maximum, and then it's going to turn around and then basically do something like this. Okay? This quantity here, at least where this thing has the highest amount of probability, so this is where the probability is equal to a maximum. This is what's known as the V sub p, which is known as the most probable velocity. So basically it just means that what? Given a particular distribution, now this thing is actually temperature dependent. So as temperature changes, this distribution actually changes. So for different temperatures, I then have a different most probable velocity. Around here, this corresponds then to the average velocity. So this is the average. And then right about here, this corresponds then to the RMS velocity, okay? Which again is equal to the square root of the square, or yeah, the average of the square. Okay? So this is what we call the RMS velocity. So basically all this thing says is what? Given a particular temperature, we can then determine the RMS velocity, the average velocity, and as well as the most probable velocity. But it doesn't mean that any one of these has all of the particles moving. It just means that the most probable has the most number of particles moving at this speed, followed then by the average and then by the RMS. But I can have anywhere from basically 0 all the way out to particles which are moving at infinite speeds. Now, technically they can't move at infinite speeds because we have special relativity to worry about. Let's not worry about that here. But again, this distribution is actually temperature dependent. So as temperature goes up or down, basically this thing is going to shift in one direction. So as temperature goes down, this thing shifts this way. As temperature goes up, it actually shifts in this direction, which we can see from here, right? Because as the RMS velocity goes up, well, it goes up as the temperature actually increases. Okay. So this is what we call the RMS velocity. So the RMS velocity is the square root of the square, or the average of the squared velocity. So this kind of gives us an idea of what type of velocity that we're actually talking about. So again, it's not the most probable, but it is a fairly probable one. Does have a good majority of the particles actually moving within it. So again, what do we learn from this? So what we learned from this is, again, microscopically, what we measure to be pressure is simply equal to the average force per unit area of these particles colliding against the wall. So these particles colliding against the wall, pardon me, which means that the wall feels exactly the same amount of force, just in the opposite direction. So that's the pressure that the wall is actually feeling. What we also learned is that this pressure goes up as the volume decreases, because we know the pressure is inversely proportional to the volume, and that what? The pressure times the volume is equal to a constant, which is equal to roughly the average kinetic energy that these things are feeling. So again, as the average kinetic energy goes up, then the pressure goes up, which means that the pressure times the volume actually goes up as well. And then finally, the last thing we learn is that temperature then is actually directly proportional to the average kinetic energy. Now, is at this stage, usually if we had class actually at USI, I would take you guys outside and blow up a garbage can. I'll have to see if any of my old students still have that video, because I know a lot of people love videotaping that. If they do, I'll post that up so you guys can actually see that. Basically, all we do is we take a little bit of water, put it in the bottom of a garbage can, take a bottle. So basically, something like this, actually a much better quality bottle than this one, like a nice Coke bottle or something like that. Plastic bottle. Fill it up about this much with liquid nitrogen, and then basically put it in and let it explode. Now, the reason for that is, what happens is I have a transfer of energy from the water into the liquid nitrogen, because basically the water is going to be around 290 to 300 Celsius, where the liquid nitrogen, actually not Celsius, like 290, 200 or 300 Fahrenheit, or sorry, Kelvin. Wow, can't speak today. And then the liquid nitrogen is usually about 70 Kelvin. So there's a nice big temperature difference between the two. So basically what happened is I get a transfer of energy from the water into the liquid nitrogen, basically causing it to boil. As it boils, the pressure on the inside goes up. As the pressure goes up, because the kinetic energy of the particles goes up, that eventually causes it to break the surface tension then of the bottle, which results in this beautiful type of explosion. But anyways, this is what we call kinetic theory. So again, kinetic theory is simply dealing with the microscopic version of the ideal gas law. But again, all of this is the ideal gas law. So we'll do one quick example of this basically in the next video, and then we'll move on to the next section.